In this video, we're going to introduce the dot product of two vectors. So let's say we start with two vectors u and v, and we will actually want to try to figure out what's the angle between those two vectors. Okay, so in this picture here, I've got the vector u, I've got the vector v. The angle that we're always going to use between two vectors will be the smaller of the two that I could possibly form. I've got this one here, or I've got going around the other way. Okay, I've got a couple of different angles that I could think about measuring. I've got this one that's on the quote-unquote inside here, and the one that's on the outside here. The inside and outside aren't necessarily making sense in terms of just having two vectors, but I've got this smaller angle in some sense than this bigger one here. We're always going to be looking at measuring the smaller angle between the two. So this is always going to be between 0 and pi in radians. All right, so to get this angle, we're going to use our knowledge from trig. We're actually going to end up using the law of cosines. So I'm going to complete the triangle. I'll go from tail to tail here, going in this direction. And now that I've got my arrow in this direction, I've got this backward. This would be v minus u with the arrow going in this direction. I apologize. For the purposes of what we're doing here, that doesn't matter, but if I want to use u minus v, my arrowhead should be on the other side. I apologize for that. I drew it incorrectly. When we do the difference of two vectors geometrically, when we connect the tips and then put an arrow, it's always pointing towards the one that comes first, not the one that comes second. So I've got my arrow in the wrong spot. My arrow should be down here. Again, not important for what we're going to do for this problem. So there's no reason for me to go and redraw that whole triangle because we literally just want the triangle. I'm not worried about which way the direction arrows are pointing. All right, so from law of cosines, we know that the length of the side squared, that's opposite my angle. So go back to the picture. The length of this side for u minus v squared, that's opposite this angle. So this is the one I'm interested in, is equal to the sum of the squares of the other two sides. So if I ignore this part on the end, this looks like the Pythagorean theorem. And in fact, if u and v are orthogonal to one another, the angle between them would be pi over 2, and this term would go away, and you would get exactly the Pythagorean theorem. If they're not orthogonal, of course, then we've got this term on the end that we'll need to subtract off, which is minus 2 times the product of the length of the other two sides times the cosine of the angle between them. Remember, again, the whole motivation for doing this is to find the angle between them. So we're going to solve this for cosine of theta. Magnitude squared is going to be the sum of the squares of the components of each of the vectors. So u minus v was x2 minus x1, y2 minus y1, z2 minus z1. So we're going to square each of those components and add those together. Likewise, we need to do the same thing for the components of u and the components of v. Now, I'm not going to worry about computing magnitudes over here. I'm going to leave that in my formula at the very end. So now let's FOIL out each of these binomial squareds. x2 squared minus 2x1 x2 plus x1 squared. Same thing for y2 and y1. Same thing for z2 and z1. Now we notice we have the same terms on both sides of the equations in several spots, right? The x1s will cancel, the x1 squareds will cancel, the y1 squared will cancel, and so on down the line. Everything that's here in the first 6 terms on the right-hand side will cancel with those same 6 pieces on the left-hand side. So after we cancel, we're left with negative 2x1 x2 minus 2y1 y2 minus 2z1 z2 equals the negative 2 times the product of the magnitudes times the cosine of the angle between them. Well, I can factor out a negative 2 on the left-hand side. Actually, first I divided here when I typed this up. But divide both sides to solve for cosine of theta. Remember, again, that's what we're trying to find is the theta. I can factor out a negative 2 in the numerator and cancel it out with 1 in the denominator. So I'm left with x1, x2 plus y1, y2 plus z1, z2 in the numerator And we recognize that as an expression that's probably pretty important for us because we already know how to do magnitude. So we actually call that the dot product. And if you've seen dot product before, you may have even seen that as the definition of the dot product first. This is motivating it in the other direction. We're trying to find the angle between the two vectors, and then we see that we need to make this computation in the numerator, so we're going to call it something special and call it the dot product. There's a couple of other names that you see for dot product. We'll say dot a lot, but you may also hear the term scalar product, because notice it's taking these two vectors, the u and the v, and making a scalar, a number. It's no longer a vector, so that's why it's called a scalar product, because the answer is a scalar. The answer is a number. You may also hear it called an inner product, and that becomes more important later on if you take linear algebra and look at, say, inner products defined in different ways, maybe on functions rather than your normal, what you think of components of vectors. All right, so let's do an example. Let's say we have the vector u is 152 and the vector v is -304. Let's say we want to find the angle between those two. Do the same thing for the other vectors, u and v here, and then the last one there. So let's do part one first. By the definition we just came up with the previous slide, we just need to multiply the same components together and then add the results. Product of your x coordinates is 1 times -3. Components is 1 times -3. For the y coordinates, y components, it's 5 times 0, and the z components is 2 times 4. So then add those together and simplify, and we get 5. For the vector u equal a negative b0 and v equal to bac, we would have a times the b, and then minus b times the a, plus 0 times the c, and no matter what a, b, and c are, that's going to always simplify to 0. 3 asks us to use the other form of the derivation of the product. We had the dot product now in terms of the dots, but if we go back and look at the previous slide, remember cosine of the angle was the dot product over the product of the magnitudes, or we can say the dot product is the product of the magnitudes times the cosine. Well, we're given each of the magnitudes and the angle, so in this case the dot product is going to be 4 times 7 times the cosine of pi over 3, and that simplifies to 14. If we have non-zero vectors to start with, then certainly the lengths of those vectors, the norms of those vectors, is always going to be positive. So if we have a dot product, in this case that's equal to 0, then the only way the dot product can be 0 is if the cosine of the angle between them is 0, right? Because here is a way to formulate the dot product. If these two are non-zero and this is 0, then this had to be 0. Well, that's only going to happen if your theta is equal to pi over 2. Remember, we're adopting the convention that theta has to be between 0 and pi. So the only time that happens for our purposes is at pi over 2. Or if the two vectors were perpendicular to each other. So we now, using the dot product, we have an easy way to calculate whether or not the vectors are perpendicular. So notice in the second part of this example, those two vectors had a dot product of 0 no matter what a, b, and c were. I mentioned that before. So that tells us that those two vectors are perpendicular to each other no matter what we plug in for a, b, and c. We also, in this case, using the dot product being 0 to tell us whether or not they're perpendicular, by this definition, the 0 vector will be perpendicular to every other vector. We typically, for vectors, stop using the word perpendicular to describe them, even though it's a nice geometric description, and we call them orthogonal instead. All right, so let's do an example with this. Let's say we want to show that, So we'll see we want to find all the values of k, so that the vectors k3, -5, and k, -2k, 11 are orthogonal. All right, well, in order to be orthogonal, the dot product of the two vectors has to be 0. Taking the dot product, we get the equation now, k squared minus 6k minus 55 is 0. That factors nicely as k plus 5 times k minus 11. So k would have to be negative 5 or 11. So for those two values, the vectors are orthogonal to one another. So let's move on and talk about some special angles and then the cosines of these things, which are called the direction angles and the direction cosines. So the direction angles, by definition, are the angles that the vector makes with each of the axes, the x, y, and the z axes. So if we have the vector x, y, z, well, I can look at the angle between v and the vector I, which points along the unit vector that points along the x-axis, and that will be a way to find the angle that v makes with the x-axis. So here's our formula for cosine of alpha. Well, now that we have the fact that we're doing v dotted with I, the 1, 0, 0 vector, well, certainly the only component we're going to get here is x, and then the magnitude of I is 1. So we get x over magnitude of v. Likewise, if we do the same thing, but for j, we'll get y over the magnitude of v. Do the same thing for k, we'll get z over the magnitude of v. So alpha is going to be your angle between v and the x-axis. We can compute it in this fashion. Beta will be your angle between v and the y-axis, and gamma will be the angle between v and the z-axis. Without solving for without solving for alpha, beta, and gamma, and just leaving them as the cosines of those things, that's what we refer to as the direction cosines. All right, so let's say we want to find the direction cosines and the direction angles of 1, negative 2, 4. First, let's compute the magnitude, because that's what goes in the denominator. 1 squared plus negative 2 squared plus 4 squared gives us 21, so we get square root of 21 for our magnitude. So the direction components, the direction cosines of each of them are the respective components divided by the magnitude. So for the cosine of alpha, for the direction cosine for the x-axis, we have 1 over root 21. For the one for the y-axis, for beta, we have negative 2 over root 21. For gamma, we get 4 over root 21. Now if we want the direction angles, we take the inverse cosine of both sides. So alpha is approximately 77.4 degrees. Beta is approximately 115.9 degrees. And gamma is approximately 29.2 degrees. You could also describe those in radians. I just happen to do them in degrees for this example. All right, another thing that we want to do is talk about is projections with a dot product. So here's what we mean by projection. So here's a vector v, here's a vector u. I'm going to take the tip of u, and I'm going to look at the perpendicular line that goes through the tip and is perpendicular to v. So we're going to drop this down, or what we call project it, down onto v. So it's perpendicular or orthogonal projection. So there's another thing that's called as orthogonal projection. So we're basically, from this point, making this right triangle and then looking at how long this side is, the length of that side, and then the vector that forms that side is what we mean by the projection. Let's denote this projection now by p just to keep things a little bit simpler. And we're going to denote the angle as theta. What we're interested in doing is figuring out a formula for p. Okay, that's what we're going for. And then we'll come up with a notation. But just for right now, we're going to use p to denote the vector just to make our lives a little bit simpler. Well, we have a way to compute the angle between the two vectors. We know that u dot v is magnitude of u, magnitude of v times cosine of theta. Well, we also know a way to calculate cosine of theta. We've formed a right triangle. So cosine of theta has to be the length of this side, the length of the adjacent side, over the length of the hypotenuse, or magnitude of p, over magnitude of u. Notice your magnitudes of u's cancel. We can solve for magnitude of p and get u dot v over magnitude of v. That magnitude of p we call the component of u along v and denote it as COMP sub v of u. So u is the thing that we're projecting, v is what we're projecting onto. Okay. All right, so to figure out what p actually has to be, let's first find a unit vector of v, a unit vector in the direction of v, which we can do by taking v and dividing it by its magnitude. So then p has to be how long p is. That's what the component of u along v is. It's the length of the projection. It's how far in the v direction u goes. And then multiply by a unit vector in that direction, because that doesn't change the length of it anymore. And now we get u dot v over magnitude of v squared times the v. And another way to write magnitude of v squared is just v dot v. So this formula we denote by proj sub v of u. And that's the projection of u along v, or onto v. So this will be the formula that we'll use to calculate this projection. So in this problem, we're asked for the vector u equal 1, 6, 2 and v equal to negative 2, 1, 2. We're asked to calculate the component of u along v and the projection of u onto v. So just using the formulas that we just came up with, we'll do the dot product of the two vectors and divide by the vector, the magnitude of the second vector, the one we're going onto. So the dot product is 1 times negative 2 plus 6 times 1 plus 2 times 2. And the length of v is square root of negative 2 squared plus 1 squared plus 2 squared. That simplifies to 8/3. For the projection, that's u dot v over v dot v. U dot v was 8. V dot v is the square of the magnitude. Well, we already calculated the magnitude was 3, so the square must be 9. So we get 8/9 of negative 2, 1, 2. And we can distribute that through if we'd like to get the vector negative 16/9, 8/9, 16/9.